Hello, everybody. So I'm not going to talk about science that's been done with CFHT. I'm here because we want CFHT to join in the next part of the experiment. We want it to use it to bring it in to get the imaging data that we need. So there's going to be a series of 3 talks introducing DESI. I am going to start off with the general introduction, and then Christoph and Dustin will take over. So I am co-spokesperson for DESI, which means I'm contractually obliged to show this slide. I actually have to tell people off if they don't include this slide. So you've all now seen this slide. DESI is a big collaboration. It involves a large number of institutes around the world and a large and diverse group of international people. We are performing a 3-dimensional galaxy survey, which means we don't want to have to worry about photometric redshifts. We want to get spectroscopic redshifts so we can find galaxies in 3D and we can understand the universe. The universe has a lot to tell us. Each one of these little dots is a galaxy. This is just the structure around us. DESI goes out at huge distances. So we need to find the galaxies to target for spectroscopy, and we do that with the imaging data. In fact, DESI used 3 different surveys. In the north, it used the BADS survey using the BOG telescope and GR bands, and it used the MALE before DESI. There was an imaging camera, Mosaic 3. We used that to get the Z band before it was decommissioned and the DESI multi-object spacecraft was put on the telescope. We also used the WISE satellite to get the near-infrared data. Maybe if I sit down, that will be better. Okay, the images that were combined with Tractor, Dustin can tell you a lot about that. Talk to him about it if you want. And then all of the imaging data was made public. Then we went over to spectroscopy. Basically, DESI, the main part of the hardware development was a new multi-object spectroscope on the top-end ring of the MALE telescope. This is 20 times better than the Sloan telescope. There was 5 times more fibers, and it's on a 4-meter telescope, not a 2.5-meter telescope. That means that what the spectroscopic survey we could do with the Sloan telescope in 5 years, DESI can do in 3 months. So this is a huge leap forwards. Basically, it's one of those times in your life which you realize you spent 5 years working on something, and now you can do it in just 3 months, which is just amazing. So the first data is now available out there. We've released 5.7 million galaxy redshifts as of March this year as data release 1. We're aiming in total for greater than 50 million redshifts. So just to give you a visual image of that, this was the SDSS. This was DESI after 7 months, at which point it had obtained more spectra than had previously been obtained of galaxies than had previously been obtained in all of human history. And it just kept on going since then. So this is the footprint of observations that was released in March, and you can see how DESI is built up. Each one of these circles is a pointing of the telescope. The color scheme tells you how many passes were there for these data, and you can see it gradually building up the data. This is what's public, and this is actually what we're analyzing at the moment. This is what will become public in data release 2. It will become public, we don't know exactly when, but roughly 6 months after we release our final key papers from these data. So nearby, that is the redshifts up to around 0.5, 0.6, we have the Bright Galaxy Survey. Then we have luminous red galaxies, emission line galaxies, and quasars as we go out in redshift. And then at higher redshifts, we're looking at getting the distribution of matter in the universe from the absorption features in Lyman alpha forest to distant quasars. So these are the numbers. They're phenomenal. This again hits hard how much time I spent on the Sloan Digital Sky Survey when you've got here just at data release 1, a factor of 10 more galaxies. It's just amazing. I only have 10 minutes, so I know there aren't too many cosmologists here, but we're going to use Barron acoustic oscillations to measure the expansion of the universe. Barron acoustic oscillations, features in the galaxy distribution set up in the early universe, You don't need to know the details. All you need to know is that basically there is a preferred separation of galaxies in the universe. There are more pairs of galaxies separated by 100 megaparsecs than there are by 80 megaparsecs or 120 megaparsecs. So once you've got a galaxy survey, you can count pairs as a function of the separation of the galaxies, and that's all you need to do to find the BAO scale. It's incredibly robust. It's very large. 100 megaparsecs expands with the expansion of the universe. So you've got that standard ruler that you can use to track the distance redshift relationship. And we can do that in DESI in incredible detail. All of our samples that we looked at have very strong detection of this BAO feature. We basically, the game is to centroid this BAO feature, find out exactly where it is at different redshifts, and then you've got the distance redshift relationship. You've got what's basically a really robust Hubble diagram, you can think of it, telling you the expansion of the universe. And we did that, and we fit lambda CDM. We did it in a blind way. If you're ever doing an experiment and you get a chance to do it in a blind way, blinding is phenomenal. I don't care if you believe that blinding or not gets rid of confirmation bias, but blinding allows you as a collaboration to sit down in a room and have the 100 or the 200 most interested people and then show them a plot that they've never seen before to tell them what they've worked on for many years. And the excitement is actually worth the whole procedure of blinding. Anyway, I'm going off on a complete tangent. We did this. We fitted lambda CDM to it. We were all very happy. This lambda CDM, which we all teach our students in fourth year cosmology, works really well. And then we looked at the parameters of that lambda CDM model, and we found that they were a little bit different from the cosmic microwave background parameters of the lambda CDM model. And all of a sudden, as co-spokesperson, I had a headache because now we have to try and explain why we're not getting the same as Planck. Everybody thinks Planck CMB is wonderful. It is wonderful. But if you don't match it, the onus is on you to explain why. We don't know why we don't match Planck. The difference of Planck, if we fit different models, is between 2 and 3 sigma. And basically, we get a lower matter density, and Planck gets a higher matter density. The other way around. We get a higher matter density, Planck gets a lower matter density, and we don't know why. One of the, there's a coincidence that we actually lie on the theta star degeneracy. I won't go into any more detail. One of the possible explanations for why we get different parameters from Planck is that lambda is wrong. If the universe expands in a different way, then what you can have is the projection to the cosmic microwave background and the projection to the galaxies in DESI can be different from the lambda CDM projection, and you can bring those matter densities back into agreement. And in fact, if you do this, you also get better agreement with the supernova data, depending on exactly which supernova sample you include in the analysis. At the moment, this is the best physical explanation that we have for the difference between DESI and Planck. If you don't like this explanation, then you need to have some large statistical fluctuation or some systematic in one of the data sets at around the 3 sigma level. If this is the explanation and the universe is behaving with its expansion rate, its accelerated expansion rate that doesn't look like lambda, then we think that actually dark energy started off stronger and is now weakening, but has an average component which looks a little bit like lambda. This means that it has, if you talk to theoreticians, talk to them about phantom crossing, negative energy states, we are observers, so we're kind of happy with this, but this crossing of -1 is a very interesting feature in these models. So yeah, there we go. Acceleration started earlier than in lambda CDM, and it's lower than lambda CDM in present, if you believe that this discrepancy we're seeing has a physical explanation, and that physical explanation is because of dynamical dark energy. Okay, that's 10 minutes. I hope I've at least convinced you that for cosmology, DESI is an amazing experiment. Give me more than 10 minutes, I can tell you all of the other things we do. We do galaxy formation, we do stellar populations, we have lots of spare fibers, particularly towards the end of the project when we've observed all of the galaxies and we're really just looking at overlaps for galaxies. We have all these spare fibers that we allow other programs to use. There's a whole range of non-cosmology results going to be coming out of DESI soon. The BAO measurements have revealed problems with lambda CDM. You can choose your poison, systematic, statistical fluctuations, dynamical dark energy. Nobody likes negative neutrino masses. Ask me about them if you want to. but it is a possible explanation that nobody believes. DESI is going to continue to the end of 2028 with a main survey. DESI is not just the male telescope. Many other telescopes contributed to the imaging data. And so now we're looking to DESI 2, and we're interested in getting the CFHT community involved.
Thank you. Questions? I have one. On your plot on the plot on the results. Yeah. Where you should go next in terms of surveys, because you have much larger errors at low Z. So is it just a matter of volumes that you cannot beat? So you have just the volumes that you have?
Yes.
So you cannot reduce the error bar?
This is a trade-off, exactly, as you say. Dark energy does something more interesting at low redshift, but that's where the observable universe is smaller.
Yeah.
So actually, you can probably get more information at higher redshift, where you can look at a larger volume. The differences are smaller, but you've got the larger volume. And that's a trade-off we play. But yes, it's pushing us to higher volume.
But at least if you have a telescope in the north and in the south for the spectroscopy, then you can still beat a bit.
That would help, yeah.
That will help.
Yeah. I mean, is there anything to be sampled still between redshift 0 and 1?
No, the illusion line galaxies go out to redshift of 1.7. It's in a tail or so. Yeah. And then we've got the Lyman Alpha Forest. So I didn't include that plot in my cut down to 10 minutes plot. I can show you later. Yeah. Euclid is still better, redshift 1 to 2. Don't panic.
A quick questions again. When you compare different investigation at different redshifts, so you're combining different galaxy populations. So is the bias an issue on that?
No.
Source of errors?
This is one of the wonderful things about the Baronic oscillation feature. This feature just comes out by eye. Bias moves it up and down. What you're really worried about is things that move it left-right. And there's very little in the universe that on the scale of 100 megaparsecs for separation of two galaxies will move them relative to each other in a biased way.
So thank you.